When we think about the balance of compute and money across the pre-training and post-training stages, what we're seeing is the pre-training stages are getting bigger, but if you look at all of the latest reports, the interesting stuff is the extra data that they're adding. So just getting better data in the pre-training stage seems to be where the art is, or the innovation. It's expensive, and so at Berkeley, I can't afford to do pre-training, but if anyone has money, let me know. We're not doing a lot of pre-training here. Post-training is far less expensive, but it kind of can be as expensive as you want it to be. So post-training, those stuff we do here, we spend a few $1,000s to do a post-training experiment. A lot of that money is actually sitting there running rollouts. So let me try to solve this problem again and again and again and again. And all of that, writing down all of my answers or trying all the different coding solutions is expensive. And then, from the few that succeed, I learn something. So we do a few gradient steps, but a lot of it is inference compute. What we're finding now is as people race to do things like software engineering, even more time is spent spinning up Docker images, running the compute infrastructure. So it's weird that even the machine learning part, both the training and inference, isn't necessarily the dominant bottleneck. And this has actually historically been true with robots as we've tried to train algorithms to control robots. The robot time itself was actually the most expensive thing. In terms of cost, it is still true pre-training is intensely expensive, and that's GPU resources at scale. Post-training is interesting in that it isn't all GPU bound, and that we have a lot of other challenges in the space of post-training. It is much more accessible though, and so organizations should start to experiment with post-training today.